4G LTE technology is designed for broad coverage, utilizing lower frequencies that travel long distances to connect our devices. 5G marks a massive leap. It employs higher frequency millimeter waves and MIMO technology, creating a dense grid capable of massive device capacity. Unlike its predecessor, 5G offers ultra-low latency and significantly faster data rates, enabling the next generation of interconnected IoT devices. 5G technology provides a massive leap in performance. It offers speeds up to 100 times faster than 4G and dramatically lower latency, which is the time it takes for data to travel. On the left, 4G takes significantly longer to load large files. On the right, 5G processes data nearly instantaneously. This performance enables real-time applications that were previously impossible, such as autonomous vehicles, remote surgery, and high-fidelity cloud gaming. The 5G revolution relies on millimeter waves. Unlike 4G, these waves have a very short range, necessitating a fundamental change in our infrastructure. To maintain coverage, 5G requires a massive increase in density. We shift from sparse, large towers to thousands of small, short-range cells. This heightened density means significantly more materials for construction, increased energy demands for grid maintenance, and a much larger physical footprint in our urban environments. While 5G technology is technically more energy efficient for every individual bit of data it transmits, the reality of its energy consumption is different. Base stations require massive antenna arrays and constant high-speed data processing, which consumes significant power. As network traffic scales, total consumption rises. Even as efficiency improves per packet, the sheer explosion in total data demand leads to a sharp increase in the network's overall carbon footprint. Building millions of 5G small cells and upgrading global hardware requires a massive influx of raw materials. Components like lithium for batteries, cobalt, and rare earth minerals are essential for high-performance 5G devices. These resources are obtained through energy-intensive mining, which often leads to significant ecological degradation. Massive mining projects disrupt local habitats, consume vast water supplies, and permanently alter landscapes. The environmental footprint of sourcing these materials highlights the growing conflict between digital scaling and sustainability. The rollout of 5G infrastructure is driving a cycle of planned obsolescence. As network standards advance, millions of perfectly functional 4G devices are being rendered outdated by design. 5G requires specialized modems and hardware to handle high-frequency signals. These components cannot be added to existing 4G phones, forcing consumers to replace their entire device rather than upgrading a single part. This transition creates a massive spike in electronic waste. When millions of devices are discarded simultaneously, they pile up in landfills, often overwhelming existing recycling infrastructure. These discarded devices contain toxic heavy metals like lead, mercury, and cadmium. Improper disposal risks leaching these chemicals into soil and groundwater, making recycling a critical environmental challenge. The industry is adopting AI to manage energy demand dynamically. During low traffic, base stations enter an intelligent sleep mode, drastically reducing power consumption without dropping connections. Network operators are increasingly sourcing energy from renewable fields. Solar and wind power are being integrated directly into the infrastructure to power the hardware components of our digital landscape. These combined efforts aim to neutralize the environmental impact of 5G expansion. By optimizing traffic, switching to cleaner power, and enhancing hardware, the vision of a green 5G becomes a reality. We stand at a crossroads where 5G connectivity drives unprecedented innovation, yet brings substantial environmental costs. Our technological evolution provides essential progress, but we must weigh the convenience of ultra-fast connectivity against the accelerated hardware consumption and energy demands of our planet. Does the convenience of ultra-fast connectivity justify the environmental cost? The balance between innovation and our Earth is ours to define.